Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry, and we have been discussing on the application of stable water isotopes in the hydrosphere and in the global hydrological cycle. And in this particular lecture we are going to see some more applications and how we understand more about our hydrosphere using our stable water isotope data, that is δ¹⁸O and δD. So, one of the most remarkable, so in our previous lecture I showed you a plot of the global map and I talked about the GNIP program, that is the global network for isotopes in precipitation, and you could see that we have a huge record of precipitation data, and not only precipitation data, we have a huge network even for a river water, that is surface water data, lake, any other kind of collaborator if they are providing more type of samples such as ice, snow, groundwater, etc. So, that kind of data is also available. So, it is a huge record and these are traditional isotopes. So, this kind of studies has been going on since the late 1950s and 60s, and we are going to today discuss a little bit about the global meteoric water line. So, one of the most remarkable correlation that exists in natural samples in earth is this particular correlation between the δ11O and the δD of a water sample. So, here you are going to see a plot of the δ11O, okay, and in this axis we have the δD, and plotted is a huge number of samples, but all from precipitation. So, these are all meteoric waters, that is rainwater. Okay. So, all the rainwater has been plotted, and you see there is a very strong correlation between the δ11O and the δD, and this is one of the very remarkable correlation that naturally exists. Okay, it naturally exists in earth system. Okay, and this was first identified in 1950s, but it wasn't understood why. Okay, it wasn't understood why do we have this correlation, but the recognition was extremely important, because in those days using a single instrument for calculating both δ11O and δD was very difficult. So, you had different isotope ratio mass spectrometers that is going to analyze 18 oxygen and δD. Okay. So, for the community, having this kind of relationship was a great idea, because now if you had a δ11O value of your rainfall and you know what is the meteoric water line equation. Okay, if you know what is the meteoric water line equation, you can calculate the δD value with a good confidence level. So, this kind of recognition of the linear relationship between the δ11O and δD is it was a huge it was a huge discovery, and in Craig 1961 he gave this meteoric the first generalized meteoric line equation, that is δD equal to 8 into δ11O, 8 times δ11O plus 10, and later in Rosansky in 1993 he modified the equation. Okay, and now we are going to use this equation, that is δD is equal to 8.17 times δ11O plus 10.35. Okay, and this is coming from thousands of samples, thousands of analysis of precipitation samples, specifically by the International Atomic Energy Agency or the IAEA. Okay. And they have very strong analysis data sets. Okay. So, there is nothing, there is no doubt on the data. So, it is no kind of instrumental bias or anything, or nothing like that. It is just how it is. And when we are going to understand, okay, why do we have this kind of collinearity, there is some kind of explanation that is related to the vapor pressures, okay, and how the vapor pressures fractionate these isotopes, that is deuterium and protium, 18 oxygen and 16 oxygen, during cloud formation and rainfall events. So, when you are going to have a water molecule, that is D218 oxygen, and when you are going to have a water molecule which is something like HD and 16O, and another molecule say which is having HD and 18 oxygen. So, these are three different types of isotopologues, and these isotopologues, their differentiation can depend on the vapor pressure and how that even in the small small differences in masses, the small differences in the masses can lead to its fractionation, okay, can leads to its fractionation during a physical process such as condensation. So, due to that equilibrium process, we are going to see this linearity, and we see that there are two different lines. One is called the global meteoric water line, which is the averaged or the weighted average of the local meteoric water line. So, there are multiple local meteoric water lines which has been averaged here to come down to this equation. And when we are plotting, the first thing when you are going to use stable water isotope data, just to check your data accuracy and any other processes that may have compromised your samples, you are going to plot this first plot. So, whenever you are working with samples and you have stable water isotope data, the first thing that you are going to do is you are going to plot delta 18O versus delta D of the data, and you are going to plot the global meteoric water line. So, giving this equation. Okay. So, using this equation you are going to plot the global meteoric water line, and if you know the local meteoric water line, you also need to plot that on your data, and you should see how your data plots. Okay. If your data is more of precipitation and all, you should know that they should fall very close to the local meteoric water line, and even very close to the global meteoric water line. Just just a few processes such as evapotranspiration, humidity and all can cause a little shifts. So, there can be some shift from the global meteoric water line, but it should fall close with the local meteoric water line. If you see some kind of differences, then you may have to reconsider your data and just check whether there was any way in which the samples were compromised, or in any way that the data during its generation in the instrument got compromised or not. So, having this relationship is a huge benefit, because it also allows us to check for the accuracy of a data set. And since there is a specific agency like the IAEA, which has this kind of support, which has all these thousands of data, and you can always request them to provide you with the local meteoric water line if you cannot find it in the literature, because they generally have all these global data sets, and you can easily find it out for your own study. Okay. Having said that, let us move into why we are a particular feature that we are going to see in this plot, and that is the difference in where SMO lies. So, SMO is the mean oceanic water composition, and that does not fall on the meteoric water line. I mean, not that it is supposed to fall on the meteoric water line, but often thinking that all the meteoric water, all the rainwater, all the precipitation is sourced from the ocean water, one can start expecting that the ocean water should also lie somewhere here, right. But no, we do not see it there, we see it a little bit fractionated towards the side, and it is showing us a specific thing. And also for the other closed basins, okay, closed basins, for instance like the Dead Sea, the Caspian Sea. So, these are again huge water masses, basically they are seas, they are huge closed basins, and there is a lot of lot of arid temperatures, a lot of arid environment. So, there is a lot of evaporation going on, and that evaporation is leading to such kind of fractionation. Okay. So, such kind of fractionation meaning that when it is arid, when it is evaporation, when there is a lot of temperature, then the 18 oxygen also gets evaporated, and the rainfall that is happening there is also rich in delta 18O as compared to a similar a similar place, a similar latitude, or similar vapor from the similar vapor, but minus the temperature and the arid environment where it will fall on this line. Okay. So, it will fall on this line, but due to more arid, more temperature, it can so happen that the delta 18O is also getting evaporated, and therefore, this meteoric water is getting shifted towards more heavier 18 oxygen concentrations. Okay. And why do we not see SMO on the meteoric water line? Okay. And that is simply because the water vapor above the ocean is not in isotopic equilibrium with the water in the ocean. Okay. So, the water vapor which is evaporating, okay. So, this is the water surface, consider this is the water surface, the vapor is evaporating. Now, here we have different stratifications as well. So, we are just touching the surface of the ocean water is a particular layer of vapor from which we are getting the mixed layer, from which we are getting this mixed layer. And after this mixed layer, there is no more direct contact with the ocean. It is only this very, very thin layer which actually excludes, which actually separates the atmosphere in interacting with the ocean directly. Okay. So, the evaporated water is no more in equilibrium with the ocean. So, it is no more exchanging isotopes with the ocean. So, since evaporation is a unidirectional process, that means whenever there is evaporation, simultaneously it is always not condensation is not happening. So, it is a unidirectional process. Evaporation to come back as condensation, a lot of other parameters has to be sufficed. For instance, humidity has to go up, temperature has to be maintained. So, those kind of important parameters such as high humidity, temperature, wind speed, all these parameters are going to control when my condensation is going to happen. But my evaporation can be a continuous process. My evaporation is a continuous and a unidirectional process that does not depend on the temperature or humidity. Of course, it is going to increase or decrease, but it is always going on, it is continuous process and it is a non-equilibrium process. Why do you mean by non-equilibrium process? That means there is no interaction back with the liquid. Okay. The vapor that is getting evaporated, it is not going to interact back with the liquid. So, therefore, it is a non-equilibrium process. So, the water vapor above the ocean has a composition of minus 13 parts per mil, okay, in delta 18O. And if it would have been an equilibrium fractionation, that means the vapor and the water is continuously exchanging isotopes. Therefore, it is expected its value should have been minus 9.2 parts per mil, just simply because delta 18O prefers the water phase over the lighter vapor phase. So, then we are seeing the equilibrium fractionation, but in nature we are going to see that it is much more negative, it is minus 13 parts per mil. Okay. That is, it is at a non-equilibrium. Okay. And why do we see this non-equilibrium? It is because of the presence of this planetary boundary layer. Okay. It is because of this planetary boundary layer where exchanges are occurring between the surface and the free atmosphere. Now, even this planetary boundary layer can be subdivided. Okay. It can be subdivided to an area where it is very close to the water, to the mixed layer, okay, to the mixed layer and to the entrainment zone. So, after the entrainment zone, the clouds no longer do come down. Okay. And the main reasons are that evaporation is not an equilibrium process and there can be other types of fractionation involved. Okay. There can be other type of fractionations also involved. We are gradually going to answer some of these complications. In fact, given this potential for complicated boundary layer physics, if you look into this boundary layer physics, how atmosphere models and how rainfall, cloud dynamics, all this is happening, it is actually a wonder that the global meteoric waterline exists. I mean, people have found it very, very difficult to find out the correct reason why we are going to see this strong linear correlation. I mean, why it exists in the nature naturally is still debated, it is still researched, and people are continuously trying to understand the the kind of microscopic processes and dynamics that controls this observation. Okay. Now, from this global meteoric waterline, okay, we come to a value which is this value. So, this is called the slope and this particular value is given a term. Okay. So, this particular the intercept, the y-intercept in the deuterium axis is called the deuterium axis parameter. It was first time named by Danskard in 1964, and in the global meteoric waterline that was given by Craig in 1961, the y-intercept or the d value was 10. In the current it is 10.35. Okay, and this is extremely important value. Okay, the d axis is a very important parameter and it can help us understand sometimes the changes in the relative humidity, whether it is seasonal, more arid climate, more evaporation, transpiration going on. So, those kind of physical processes this d axis parameter is going to help us understand. This d axis value is mostly controlled by the kinetic effects associated with the evaporation of water at the surface of the ocean. It is more of the kinetics rather than the thermodynamics, okay, of the evaporation process. Okay. Now, this slope, therefore, you can see that this d axis value can change, the y-intercepts keep on changing, okay, and it gives us an understanding of whether it is a more evaporation, evaporation environment. Okay, what is the kind of climate, what is the kind of temperature there. Okay. So, the slope of this line, the slope of this global meteoric water line, that is 8, it is a function of the relative humidity. Okay. Whether the slope is higher, the slope is lower, what kind of slope it has. Okay. That shows us what kind of humidity it will have. If it is more humid, less humid, such things. The slope becomes shallower with decreasing humidity. If the humidity is growing low, if the humidity is getting more and more towards arid, that is basically showing us that there will be an evaporation trend. When there is an evaporation trend, what is happening? My 18 oxygen is going into the atmosphere more. Okay. My 18 oxygen is going to the atmosphere more. Okay. So, what I am going to see is this kind of shift. Okay. I am going to see this kind of shift, that there is now more 18 oxygen in the water vapor in this arid climate as compared to a region where it where it is normal humid. Okay. So, from this delta 18O and delta D graph, if you are plotting it, so the first thing, as I said, you plot the global meteoric water line, and when you plot the data, it will show you a lot of things. It will show you where your if it is, it will show you the kind of vapor source. For instance, if it falls parallelly to the meteoric water line, okay, if it is falling here, okay, if your data plots somewhere here, okay, what you will know, it is coming from a more arid vapor source. Okay. If your data is plotting more here, but parallel to the global meteoric water line, you will know that it is coming from a more humid vapor source. If the slope entirely changes, if the slope is, there is a huge shift, you will know there will be evaporative losses. There is a humidity factor coming in. Okay. There is a lot of evaporation effect, and if it is less shallower, okay, so from here to here, okay, if it is less shallower, then it is more humid. If it is more shallower, okay, if the slope comes down to here, if the lines falls like this, then it is more and more arid. So, as it is going humid, this line goes like this. As it is going more arid, this line goes like this. And there is also a seasonal difference. Okay. So, in winter, due to cold temperature, due to humidity difference, due to temperature difference, the values will be more and more negative. In summer, there is more temperature, more kinetic fractionation, but due to higher temperature, the 18 oxygen is also now high in the vapor phase. So, there is less differences between the vapor and the liquid. So, therefore, the delta 18O in the liquid will also be high, will also be more positive as compared to the winter values. So, here you will find the winter data and here you will find the summer data. So, this is more negative and this is more positive. Okay. More negative, more positive. So, if you compare, you will see that the summer data, they are more positive as compared to the delta 18O of the winter samples. Okay. Same thing for the delta D axis also. Okay. In the summer months, it is more positive as compared to the winter months. So, overall you can come down to this. Okay. So, if your samples are from a warmer area or from a lower latitude or from a lower altitude or from the coastal areas, then you will find your data is more in this region, in the topper region. if your data is from more cooler areas, more higher latitudes, more higher altitudes, okay, more inland, separated from the coast, then they will plot here. Okay. They are going to plot here in the bottommost corner. So, when you plot your data, it is extremely important that you plot it with the global meteoric water line, with the local meteoric water line, with the vapor source data if you know it, and then see how it is behaving, how the entire system is behaving. Okay. And this will give you enough information if you are looking into precipitation, whether those particular samples has undergone through any evaporative losses, whether it is coming from a different vapor source, whether the vapor source is showing any changes, any temporal changes or any spatial changes. Okay. So, humid regions will show smaller departures from the global meteoric water line than the arid regions, and generally this is interpreted as a proxy for the source of the moisture. Okay. Such kind of departures from the global meteoric water line is useful for indicating the source of the moisture. So, it is used as a proxy. Okay. Proxy means an indicator, a tracer, okay. It is an indicator. Now, what other factors control the isotopic composition of precipitation? So, we have already discussed this kind of Rayleigh, okay, this kind of Rayleigh fractionation, wherein the water mass as it is getting evaporated from the oceans, and with the gradual rainfall effect, with the gradual rain out effect, there is always a differentiation happening. There is always the different values of delta H and delta D values coming in. But other than this Rayleigh fractionation, what other factors can also cause fractionations? So, there are 6 main factors that will cause isotopic fractionations of stable water isotopes, and that is temperature, distance or the continentality effect, the latitude effect, the altitude effect, the amount effect and the seasonal effect. And some parts we have already discussed, but some of them we are going to talk about more in details, specifically about the relationships that has already been calculated, developed and very useful. Now, what is the basis of this kind of fractionation? What is the basis of the fractionation? It is that the lighter molecule species, they are preferentially more enriched in the vapor phase as compared to the heavier isotopes. So, this forms the basis of such kind of fractionation processes. Okay. So, the heavier isotopes will always prefer the stable phase, okay. And also simple difference between the evaporation and condensation processes itself, that is evaporation is a unidirectional process, it is a non-equilibrium process, okay. Kinetic fractionation can easily cause changes, and relative humidity will also cause changes. Evaporation is happening where relative humidity is less than 100%. Okay. It is a continuous process. Condensation is not a continuous process. Okay. Condensation is a equilibrium process only occurring when the relative humidity is 100%. Once that 100% relative humidity is achieved, then only condensation processes starts forming, and the vapor and the rain that is condensing from that vapor is at equilibrium. That means, the vapor composition will control the rainfall composition and they will be the same. They will be the same. It is at equilibrium, they will be the same thing. only after the rainfall falls. And there will be other factors such as re-evaporation that can cause the changes. Okay. So, we have to be cognizant about the fact that the rainfall when forming is at equilibrium, but after during its movement across the atmosphere it might get a lot altered. At 100% relative humidity, no net evaporation is occurring, no net evaporation, that means evaporation is occurring, but condensation is also occurring. Therefore, there is no net or no more evaporation is going on. Failure to attain complete or equilibrium isotopic exchange between the liquid and the vapor phases causes the oceans to be isotopically lighter, okay, causes the vapor above the oceans to be isotopically lighter than predicted from the known equilibrium isotopic fractionation at the temperature of the ocean surface. What do I mean? There is no complete isotopic exchange, right. Whenever there is equilibrium isotopic exchange also happening between the vapor and the liquid phases, there is not complete equilibrium. There is no completion of the process. It is not like the rainfall that is forming is completely in equilibrium with the vapor phase. So, it is this lack of complete or equilibrium isotopic exchange, because as soon as it is getting formed, it might just fall and it might get removed from the system. So, that completeness is never going to occur in nature. It is because of this particular reason that our theoretically calculated equilibrium composition of the vapor is never found. It is always lighter. From our theoretical equations, we are going to expect the vapor composition to be minus 9.2 parts per mil. But when we are going to take a vapor above the ocean mass and we measure it, we find the value is to be minus 13 parts per mil. So, that is the difference. This is the theoretical value considering equilibrium fractionation, and this is the real measurement. This is why SMO does not lie on the global meteoric waterline. Okay. Now, with this I come to end of this particular lecture. We are going to continue discussing this more in the next lecture. Thank you.